we're going to talk about section 2.1, systems of linear equations with unique solutions. Okay. So, if you recall, in section 1.3, we had two equations and two unknowns. And we talked about how to solve those, right? If they were both written y equals, then you could just set the other halves of them equal to each other and find out what x is, and then substitute back in to find out what y is. Otherwise, you'd have to solve one of them for one of the variables and substitute, right? So we saw this in section 1.3. And now we're going to add more variables and equations. Now, this is going to necessitate us working smarter because things get more complicated once you add more variables. So here's an example to get us started of the type of thing I'm talking about. We want 3x plus 2y plus 4z to equal 600. We want 2x plus y plus z to be 275. And we want 6x plus 6y plus 2z to be 1150. And we want all of these things to happen at one time. So, I'm sure that you've solved two equations and two unknowns before. Have you solved three equations and three unknowns before? Is this something that is familiar to you? Yeah, a little bit? Okay. So what we're going to learn is we're going to learn a method of solving these that's actually an algorithm that is built into almost any software package on mathematics that you could imagine. So, of course, it's in your graphing calculator, it's on Wolfram Alpha, it's on any sort of computer algebra system that would exist, has a way of doing this quickly. So we need to describe what this method is, right? Algorithms are great, they do our work for us, but if we don't understand what they're doing, then it's hard for us to figure out when we're getting a wrong answer and why we're getting a wrong answer. So it's important to understand how the algorithm works in order to be able to effectively use it. The method we're using is called Gauss-Jordan elimination. And there are a variety of legal moves that we can make in order to solve these equations. And there are three types of moves that can be made. The first move, we'll call it Rule 1, is you may interchange any two equations. So you can change the order in which you write the equations. Doesn't sound useful at all, but it is useful in terms of getting down to what we want to get down eventually. The second rule, you may multiply any equation by a non-zero number. Okay, this is the second rule that you're allowed to do. So you can multiply both sides of any of those equations by a non-zero number. And Rule 3 is you may add to one equation any multiple of another. And so any equation, you can take that equation and add a multiple of another equation. That's the most complicated rule, and that's the rule that's actually the most useful. Okay, so what's the point? What are we trying to do here? What we're trying to do is we're trying to start with a system of equations like we have here. And what we're going to do is we're going to perform these moves until we can get the system to look like this. 1x plus 0y plus 0z is equal to x1. 0x plus 1y plus 0z is equal to y1. And 0x plus 0y plus 1z is equal to z1. Then the solution is x is equal to x1, y is equal to y1, and z is equal to z1. So the goal is to start with something like in that blue rectangle, a 3 equation, 3 unknown, or 5 equation, 5 unknown, or 2 equation, 2 unknown, and to keep doing these 3 moves in order until we get to the first equation has just x equals. The second equation has y equals. The third equation, all that's left is z equals. That's the goal of Gauss-Jordan elimination. So I'm going to show you how this works with some examples. Okay. So here's our first example. We're just going to start with a 2 by 2 system because that's going to be easier for us to deal with. This is x minus 3y is equal to 7. Negative 3x plus 4y is equal to negative 1. Okay. The goal is to eliminate x from all the equations except for the first one. Okay. So I want to get rid of that negative 3x in the second equation. So I'm going to use rule 3 and multiply the first equation by 3 and add it to the second equation. So I'm going to remark that. I'm going to say row 3 plus 3 times row 1. Okay. Now, this is we're going to be done with this in not too long, but this is a complicated thing, and sometimes it takes many steps to get there. So it's important to be careful and write carefully. And so on the right side here, on the left side I'm going to have my progression of what I'm doing here. And on the right, I'm going to do this 3 times row 1, so I have something here so I can see what I'm doing. So this is 3x minus 9y equals 21. That's 3 times row 1. I'm writing that down so that I see it right there and I can easily add it to equation 2. So I've multiplied row 1 by 3, and I have it there to refer to. And now I'm going to write down the same system. I'm not doing anything to row 1. But row 2, sorry, why did I say row 3? I mean row 2. There's only 2 rows here. Row 2 plus 3 times row 1. So when I add row 2, which is this equation here, to 3 times row 1, which is this equation here, I get 0x. I get negative 5y. And I get 20 on this side. Okay, so it's important that you understand where this second equation came from. Okay, if you don't understand, I'll say it again. Please ask if you're confused where that second equation came from. That second equation is 3 times the first equation plus the original second equation. And now, see what I've done? I've eliminated x from the second equation. You may remember doing this from solving systems of equations before, but you may not have done it in this systematic method. Okay, so now let's figure out what we want to do. We want to get this to have 1x plus 0y equals something, and the second one I need to have 0x plus 1y equals something. So I really want 1y, not negative 5y. So I'm going to multiply row 2 times negative 1/5. It's a legal move to multiply a row by any number that I want, to multiply an equation by any number that I want. I'm using the words row here because you're going to see soon we're going to abstract, make this a little more abstract in order to clean up our work. So now I keep the first equation, x minus 3y is equal to 7. And then the second equation is still 0x. Now I'm going to have plus y. And here, 20 divided by negative 5 is negative 4. Questions about this move here? Okay. Yeah, Peter.
Are you able to just divide by 5?
Yeah, negative multiplying by 1/5 and dividing by 5 are the same thing. Yeah. We just stated the rule is you can multiply a row by any number. But multiplication and division are in fact the same operation. They work identically. Yeah. So you can think about this as dividing by 5 if you want. That's fine. Well, negative 5, right? Okay, now what I want to do, that first equation still has y's in it. The first equation still has y's in it. I want to eliminate those y's. I want it to be x plus 0y equals something. The second equation is perfect. It's exactly what I want it to be. But the first equation is not right because it still has y's in it. So here I'm going to do the move where I'm going to multiply. I'm going to take the first row, the first equation, and I'm going to add 3 times the second one. On my work over here on my margin, I'm going to multiply 3 times the second equation, so I have it written down and I don't get confused. So 3 times the second equation is 3y equals 12. And now I add that to the first equation, and I get x plus 0y is equal to negative 5. And then I have 0 plus y is equal to negative 4. So now I have my solution. X is equal to negative 5, and y is equal to negative 4. Any questions about this problem, this process? You don't have to work as meticulously as I do, but you have to work meticulously enough to not make mistakes. I recommend whenever you're multiplying a row or an equation times a number to add to another one, you write it down in scratch on the side, because it's very easy to not do that correctly, especially if we have 3 variables involved instead of just 2 variables. It can get hard to keep track of whether you've because maybe you can do it in your head, but I recommend you write it down. Okay, let's take a look at another one. And now I'm going to do a level of abstraction that's going to help us get this done a little more efficiently. So here I'm going to solve the equation 2x minus 6y is equal to negative 8, and negative 5x plus 13y is equal to 1. So 2x minus 6y is negative 8, and negative 5x plus 13y is equal to 1. So those are the 2 equations I want to solve. Now, here is an innovation that allows us to work quicker in terms of how long it takes us to write it down. I'm going to change this, instead of a pair of equations, to just be a matrix. 2, negative 6, a bar, negative 8, negative 5, 13, and 1. Okay. That bar is supposed to mean, oh, those are the constants, not the variables. So the first column of this matrix represents all of the things multiplied by x. And the second column of the matrix represents everything multiplied by y. Do we see how that matrix, we get that matrix from that equation? Is that clear? Do we see where all those numbers come from? Does that make sense? Okay, what's the innovation here is it just allows us to, write a lot less things. So now we want to make a move. We're going to take 1/2 times row 1, or row 1 divided by 2, so we can get a 1 here. And then I'm leaving row 2 alone now. So there's our new matrix. I've just multiplied row 1 by 1/2. Now I'm going to multiply row 1 by 5 and add it to row 2. So this is row 2 plus 5 times row 1. On the side here, I'm going to write what 5 times row 1 is. It is 5, negative 15, and negative 20. Just want to write that down. Now I'm not writing down the x's and y's anymore. I just want to write that down so that I don't make a mistake in doing this addition here. Okay, so now I keep row 1 the same. Now I have 5 plus negative 5 is 0. 13 plus negative 15 is negative 2. And negative 20 plus 1 is negative 19. Okay, so there's my second step. Now I'm going to take negative 1/2 times row 2 in order to get a 1 there. This is 1, negative 3, negative 4. That stays the same. 0, 1, 19 halves. That's 9.5. So I'm just going to keep it as 19 halves. Now the only thing I need to do now is I need to eliminate that negative 3 there, and then I'll be good. So I need to multiply 3 times row 2 and add it to row 1. If I multiply row 2 by 3 and add it to row 1, that will eliminate that negative 3. And on the side, I'm going to write what 3 times row 2 is. Okay, so 19 over 2. Okay, so this is 19 times 3 is 57 over 2. Right? Yeah. Okay. So I add 0 plus 1 is 1. Negative 3 plus 3 is 0. And negative 4 plus 57 over 2, well, let's see, to do some scratch here. Negative 4 is equal to negative 8 over 2. So negative 8 plus 57 is 49. So this is 49 over 2. And then we have 0, 1, 19 over 2. So now we have the solution to our system. X is equal to 49 over 2. And y is equal to 19 over 2. And we can check that if we want. We can go back to the original system of equations and check that and see if that fits, right? That's probably something you want to do on a quiz or something like that. Any questions about the second one that we did? All right. Let's do an example, at least start an example where we have 3 variables. 3x minus 6y plus 9z is 0. 4x minus 6y plus 8z is equal to negative 4. Negative 2x minus y plus z is equal to 7. So I want all of those 3 equations to be true. I want to find values x, y, and z, which will make each of those 3 equations true. That's what I'm looking for. So our first step is to transform this into a matrix again. So it's going to be 3, negative 6, 9, 0, 4, negative 6, 8, negative 4, negative 2, negative 1, 1, 7. That's the matrix we get from this system of equations. And now we need to proceed and figure out, we need to take these steps to get down to right? What we want in the end, what we're looking for is 1, 0, 0, a number, 0, 1, 0, another number, 0, 0, 1, another number. That's the goal that we want to get to, and we can see we're quite far from that goal at this point, right? Quite far. Okay. So the first thing we're going to do is we're going to multiply row 1 by 1/3. We're going to divide row 1 by 3. We get 1, -2, 3, 0. We keep the others the same. And that's our first move, is to multiply row 1 by 1/3 so that we can get a 1 in the x-coordinate. Because when we have 1, then it's easy to see what we need to multiply it by to add to the other rows. Right, this is very helpful. So our second step, let's eliminate the 4 in the second row. So it's going to be row 2 plus -4 times row 1. You can think of that as -4 times row 1. I'm going to write my scratch work of -4 times row 1 over here. So that I don't make any mistakes. And now I'm going to copy down my result. I keep row 1 the same. Row 2 is now 0, 2, -4, -4. Any questions? Or did I make a mistake or anything like that? That was good. Okay. Now I want to eliminate that -2 right here. So to do that, I'm going to take row 3 and add 2 times row 1 in order to make this work. So I'm going to write what 2 times row 1 is over here. That way I will be less likely to make an error. 1, -2, 3, 0. The second row stays the same. Now we add 2 plus -2 is 0. -4 plus -1 is -5. And 6 plus 1 is 7. 7 like this. Any questions? Okay, now this is not fun to do, right? I get that. This is a boring thing to do, but it's important to understand what's going on so that when we use an algorithm, we know what it's doing, or else we are the slave and the computer is the master. All right, looking at this now, I want to now focus on the second column. That 2 in the second column, 2, -4, -4, I'm going to divide that by 2. So I get a 1, because 1 is the easiest thing to work with. So I'm going to take 1/2 times row 2. You can see why someone would want to automate this. It's boring, and it's extremely easy to make a mistake. And once you make a mistake, it propagates through for the rest of it and totally ruins what you're doing, right? So this is a high wire act of simple algebraic manipulations, because once you go wrong, you can't really tell what you've done, and when you get down to the bottom, you get a wrong answer. That's not great. Okay, now I can now eliminate the -2 and the -5 in the second column. So to do that, I'm going to take row 1 plus 2 times row 2. And I'm going to write 2 times row 2 over here. And here we go. 1, -2, 3, 0. Oh, that's not right. That's what I'm trying to do. Okay. The 1 stays, and then we get 0 here. We get -1 here, and then we get -4 here. We get 0, 1, -2, -2, 0, -5, 7, 7. Now I want it, my target is on the -5 in the third row, so I'm going to take row 3 and add 5 times row 2. So I want to write 5 times row 2 over here. First row stays the same. Second row stays the same. And the third row changes now. 0, -3, -3. Okay, I'm getting close to what I want. Just 1s on the diagonal and 0s everywhere else. I'm almost there. So the first thing I want to do now is I want to get a 1 in that place there. So I'm going to take row 3 and multiply it by -1/3. So -1/3 times row 3. Or you can think about it as row 3 divided by 3, -3. Okay, now we're 2 moves from the end now. We're almost what we want. We are now working on eliminating these numbers there. And it's going to take 2 moves to do that. The first move is going to be, let's take row 1 plus row 3. Because the -1 and the 1 will cancel. There's no scratch work I need to do for this one because I'm not multiplying that third row times anything. -1 plus 1 is 0. -4 plus 1 is -3. Okay. And finally, I'm going to take row 2 plus 2 times row 1 to finish this up. 1, 0, 0. -3, 0, 1. Oh, I need to multiply that row. 0, 0, 2, 2. Okay. This is going to be 0, 0, 0, 0, 1, 1. There. Finally, I have what I want. I have the matrix with 1s in the diagonal and 0s everywhere else. And now I can write my solution. X is -3, Y is 0, and Z is 1. But I'm going to write down the original equation so that we can see this works. Okay, this is my original system. And substituting -3 in for X and 0 in for Y and 1 in for Z gives us 3 times -3 plus 0 plus 9 is equal to 0, which is true. 4 times -3 plus 0 plus 8 is equal to -4, which is true. And -2 times -3 plus 0 plus 1 is equal to 7, as desired. Okay, so we're able to solve that system. Now, I'm sure you've probably solved a 3x3 system before without this method with the matrices, right? And the moves you were making were pretty much equivalent moves, and then you were substituting, right? We don't do any substituting with this method. It's a little bit different than probably what you're used to. Questions about this? Questions? Okay. So I'm going to give you some work to do in a minute, but I want you to, eventually we are going to automate this process, right? Now, what I just did, that problem, the last problem that we did that took us like 5-10 minutes to do, I'm probably not going to ask you to do a whole problem like that on a quiz or a test or something, right? It takes a lot of time. It's very easy to make a mistake early in the process and get way off track and not get a right answer. which makes it very, very difficult to grade because you got to make it. It's when someone gets the wrong answer, it's very hard to figure out where they went wrong, right? So the goal is not to get so good at this that we're able to, produce exactly what I did here on a test. But I might ask you to, start this, take the first few steps or things like that. Or just a 2x2 system, you're supposed to do these things, right? That's not going to take as long. You can get through that. And eventually, we're going to learn, here today, we're always getting solutions. Sometimes you don't get solutions. So we're going to talk about that later. And then eventually, we're going to talk about how do you actually automate this with a computer or a graphing calculator or something like that. And you'll see it works very quickly and gives you the answer that you want. Okay, so to work at now, if you can take some time and make sure you can do these problems, 7, 9, 13, 23, 29, and 31. And then for the homework, 30 through 38 even, 48, 52, 58, and 67. This is not homework, but if you have a graphing calculator, I want you to look at 40 through 46 because it outlines the steps that your graphing calculator uses, or that you need to learn to do this on your graphing calculator. So if you happen to have a graphing calculator, I would take a look at those so that you learn how to do this process with your calculator. Wolfram Alpha will work fine too, and we'll use it eventually when we talk about this. Okay, I'll have the book open here, and